In this short video, we will define a field, subring, subfields, and ring homomorphisms in order to prepare for extending the natural numbers. A field is defined to be a ring F for which the set Fx, which is the set of non-zero elements of F, is also a group under multiplication. And thus a field is a ring with the additional property that whenever A is in F and A is not zero, then there's an inverse element within F such that A times A inverse is equal to A inverse times A is equal to 1. And for both rings and fields, we usually simplify this by writing AB instead of A times B. We'll also note that we can drop the parentheses in A plus B plus C into just A plus B plus C. And we can write A times B times C instead of A times B times C. We also usually write that A minus B is the same thing as A plus negative B, where negative B is the inverse element with respect to the addition operation of B. If R is a ring, then any subset S of R, S is a subset of R, is called a subring, if S is also a ring under the operation defined by R. And we have the same thing for subfields within fields. By its definition, a subring S must also contain the elements 0, 1, and it must be the case that's closed under addition and multiplication, namely that A plus B and AB is within S for any elements A, B, and S. And we must have that is closed under inverses, that negative A is an element of S for any A. In the case of fields, we must also have the case that we have multiplicative inverses, namely that A inverse is an element of S for any non-zero element A within S. A mapping phi between two rings, R and S, note that S need not be a subring anymore, is called a homomorphism of rings, or a ring homomorphism, if phi of A plus B is equal to phi of A plus phi of B, and phi of A times B is equal to phi of A times phi of B for any two elements in R, and that phi of the identity element of R is equal to the identity element of S for the multiplicative identities of R and S for these rings. Since we note that a ring is a group under addition, it follows, as we did before, that we need not specify the additive element with respect to addition because we get that guaranteed that phi of 0 sub R is equal to the 0 sub S. And additionally, we have that the inverse with respect to the additive operation is preserved under ring homomorphisms. However, since R is not a group under multiplication, it is necessary to assume the second point, that it preserves the multiplicative identity elements. A homomorphism of fields has the same definitions, and we'll just note that it should respect the inverse operations with respect to multiplication. Any two, and previous, like we did with the groups, a bijective ring or field homomorphism is called a ring or field isomorphism. That is, if two rings have a homomorphism between them that is also a bijection, then we say those rings are isomorphic. Or if we have two fields with a homomorphism between them that is a bijection, then we say that those fields are isomorphic. With that, we're going to carry on next time with extending the natural numbers into more complex algebraic structures. Thank you.